Homework 16, the central limit theorem for proportions, video 2, the sampling distribution for proportions. In the previous series of videos, we talked about the sampling distribution for X bar, and just a quick synopsis of how that went. We had a population with so many values in it, and we picked a sample size. To create the sampling distribution for X bar, we picked every sample of that size, calculated each sample's X bar value, each sample's mean, and then made a distribution that listed all of the possible X bar values and the probability that they're occurring. We can do the same thing for proportions. So we're going to build a small example with a small population. Our population is going to consist of 5 people, 2 males and 3 females. As in the previous series of videos, the only reason I use the different colors is to distinguish between these 2 males and these 3 females. I could have listed names, but it was easier to just write letters using different colors. So that way, when we pick our samples, we can distinguish between this male versus this male, and then this female versus this female versus this female. But before we do the sampling proportion, and this is something I should have done in the previous series of videos, let's calculate the population proportion of males right now. It's actually pretty easy. This population has a total of 5 people, and only 2 of them are males. So if you divide 2 by 5, you get 0.4, or 40% of the population are males. Let's make a sampling distribution of p hat with a sample size of 2. Remember, when you have a sampling distribution, you have to first start with a fixed sample size. In order to do this, we need to figure out every possible value of p hat, which means we need to figure out every possible sample of size 2. Oops, there goes the lid for that marker. We can get it. Of course, it would have to hide way back there. Where's my yardstick? Sorry, folks. I mean for the delay in the content, but if I don't get this cat to this marker now, I will forget where it is, and this marker will dry out. And this is the last red marker. Excuse me. Okay. So where were we? Oh yeah, we're making a sampling distribution for p hat for a sample size of 2. So we need to list all possible samples of size 2. Let's start with all the samples that contain the first male. So if they contain the first male, then it can either contain the second male, or it can contain any of the 3 females. The black female, the red female, and the green female. And again, the only reason I'm using different colors is to make it easy to distinguish between the different females and the different males in the sample. So there's all 4 samples that contain samples of size 2 that contain the black male. So now let's look for samples that contain anything but the black male. So let's start with the red male. Let's list all the samples that contain the red male, but not the black male, because we've already got the one that contains both. So if our sample contains the red male, then it could contain the black female, or it could contain the red female, or it could contain the green female. Now we have all the samples that contain the red male. There should be 4 of them, and there are. Now we have every sample that could contain one or both males. So let's just focus on the females. One sample that contains only females could contain the black female and the red female. One that could contain 2 females could be the black female and the green female. And we should have 10 samples. We have 9. What am I missing? Oh, the sample that contains the red female and the green female. By the way, there is a methodical way to manufacture all the samples of a certain size, but we won't get into that. And to be honest with you, I was just feigning that I didn't know which one was missing. I was giving you an opportunity to go, it's that one. All right, so here's all of our samples of size n equals 2, but this isn't the sampling distribution. The sampling distribution says, give me every possible p-hat value and the probability of a random variable equaling that p-hat value. So we need to figure out the p-hat values for all of these samples. And remember, our proportion has already been defined as the proportion of males. These are samples, so these are going to be p-hats. So for each one, I need to figure out what proportion of the sample is males. This one's easy, they're all males, it's 2 out of 2, which is 100% or just the number 1. The 3 below it only have 1 male, so each of these p-hats is 1 out of 2. So as a decimal, 0.5. And as a percent, 50%. For the next column, the first 3 also have exactly 1 male, so their p-hats are also 0.50, getting a lot of those. But the remaining 3 samples have no males at all. So the percent of the remaining 3 samples, the percent of each of the remaining 3 samples that are males is 0%. And now we can make our distribution of p-hat, our sampling distribution, by listing every possible p-hat value. Even though we had 10 of them, there were only 3 different values, 0, 0.5, and 1. And now we can figure out the probability of these occurring by simply asking how many out of the 10 samples have a certain p-hat value. For example, out of the 10 samples, how many of them had a p-hat value of 0? 1, 2, 3. So there's a 30% chance that a sample is 0% male. In other words, there's a 30% chance that the sample we select is all females. For a p-hat value of 0.5, we still have 10 samples, but out of them, 1, 2, 3, 4, 5, 6 of them have a p-hat value of 0.5. So 6 out of 10 of the p-hats are 0.5. 6 divided by 10 is 0.6. So that means that if we pick 2 people at random out of here, there's a 60% chance that half of them are male. And the final p-hat value was 1, but that only occurred once when both members were male. So 1 out of 10 of the samples has a p-hat value of 1. So 0.1. And that's the sampling distribution for p-hat. So what does this mean over here? If we think of these as percents, if we pick 2 people at random, there's a 30% chance that none of them are male, a 60% chance that 50% of them are male, and only a 10% chance that 100% of them are male. I want to do one more thing before we go to the next video. We're trying to establish a relationship between the p, the proportion of the population, and all p-hats, all 10 of them. In the original population, 40% of them were male, or 0.4. How does that relate to all 10 of these p-hats? Well, guess what you get if you average all 10 p-hats? If you average all 10 p-hats, we had 3 of them that were 0, so we would add 0 3 times, which is silly. 6 of them were 0.5, so we could add 0.5 6 times. We could have just done 0.5 times 6. 1 of them was 1, and there was a total of 10 of them. This isn't that hard to add. Each pair of halves is one whole. We can ignore the zeros. 1, 2, 3, 4. 4 out of 10, which is 0.4, which was the same as the proportion of males in the original population. So what does this mean? This means you take all the samples of a given size, in this case size 2, calculate the proportion of each sample that has a characteristic, 100% are male, 50% are male, 0% are male, and average all those p-hats, it will tell you the proportion of the entire population that has that characteristic. I know, we knew it up here. Why do we have to do all that? Because what it does is it establishes a relationship between the distribution of the p-hats with the p for the whole population. And we'll make that a little bit more concrete in the next video.